Thank you. Is it on? Yeah. Thank you, Jules. So my talk today is a deep dive into Catalyst, the optimizer of Apache Spark. Does anybody know what Catalyst is? A few hands. Okay, so it won't be completely uncharted territory then. I'm an Apache Spark committer, and I also work for Databricks. Databricks is a company founded by the creators of Apache Spark. We have written about 75% of Spark's code, and we offer a SaaS solution for our customers, and you get to work with Apache Spark, and we'll do the hard part of Apache Spark for you, the infrastructure management. My talk today, if you look at Spark, how it's layered, then you start with some data, just some JSON or some other data, and we have like the Spark core, the RED API, and you can actually do transformations on that and write programs in REDs. And then you have something called the structured part of Spark SQL. And Spark SQL uses Catalyst. Catalyst underpins everything in Spark SQL, so including SQL itself, DataFrames and Datasets, but also ML pipelines, structured streaming, and graph frames. So this begs the question, why do we need structure at all? Structure is actually quite limiting. It limits actually what you can say, but it also gives you transparency. So in the case of Spark, we want to know what the user is doing in this operation. If you write an RED operation, you just see, Spark can only see a function that maps something, that filters something, so we don't know what's going on in there. Structure allows you to actually reason about what is going on in the user program. The thing is, structure limits, but not as much. We can do, I think, there are like a few use cases in which you would need REDs. The rest you can do with structure. So, but it gives us something, structure. It gives us the opportunity to do optimization because now we all of a sudden can reason about what's happening in the program, and we can actually start doing cool optimizations. So let me drive this home with an example. Did anybody here ever write RED programs? Also a few hands. So for the ones of you who don't know how to do that, this is an example. This does something relatively straightforward, actually. So pdata contains like a department and an age. It contains the ages of a person in the department. And we want to calculate the average age within the department. Okay. So if you write an RED, so the pdata contains tuples. And if you want to count them, if you want to calculate an average, you need to keep track of two things. Three things. That's the department, the age, and the number of times, or the sum of the age and the number of times, number of records we've seen. So that's like the first line, that's the map. Then we reduce by the department, we group by, and then we count like this. Then we count the age, the sum of the ages. Then we sum the sum of the ages and the sum of the counts. And if we have that, then we can finally map that into the average age by dividing the age by the number of records. That's kind of hard to do for something relatively simple. Or we can use DataFrames. That just group by the department and takes an average. Or you can do it by SQL, using SQL. Thing is, what makes it special is that actually those two representations, so DataFrame and SQL, are exactly the same under the hood. The syntax is different, but Spark SQL doesn't know the difference between those two. But because the structured API provides us with another thing. So this is more concise, this is more clear, your intent is much more clear, but also gives us a lot better performance. Spark SQL versus a regular RED, you see that the two, the SQL and the DataFrame are both performing equally good. And the RED, that just takes twice as long. That's because we cannot, because the user is responsible for making that program go fast. So how do you write programs using structured APIs? Use the high-level data, the high-level interfaces. And I mean by that is just use the APIs we provide you and use like the constructs we have. And actually, to drive it home, just use SQL, DataFrames, and Datasets. And then we need something else, because now we have like something which is very high level, and we need like a program which is actually clever enough that rewrites your program into something much, much more concise and much faster. And that is this. Catalyst. Catalyst helps you write your programs faster. So what is Catalyst? What does Catalyst look like? So you take a SQL AST, a data frame, or a data set, or some Python frame, or an R frame, and they all get translated into a thing called a query plan. And Catalyst analyzes that query plan, makes sure it optimizes it, and then produces an actually RD code in the end. A bit more deeper way of looking at Catalyst is that you have like this thing called, you have like this pipeline, and that consists of an analysis phase. Analysis phase means that we are going to check your plan for errors and see if it's okay, if it's semantically valid. But we're also going to resolve tables, columns, functions. And if a plan survives analysis, then we're sure that it can be executed on Spark SQL. If it's not, then we throw in an exceptions. Then we go to optimization. In optimization, we apply all kinds of heuristics and transform the logical plan to make it better, make it faster, do clever stuff. I'll show you a lot of examples in a little bit. And then we have physical planning. Physical planning means that we go from this high-level plan to an actual executable plan. And we do that by generating a multitude of plans, applying a cost model, and then just selecting the best plan. So Catalyst, same picture as before. We get the query plan, we apply transformations, and we get an optimized plan. When we have an optimized plan, we are going to do a lot of code generation, especially in 2.0. If you went to Samir's talk, you should have seen a lot of that. And finally, we end up with some super optimized RED. But we need like a common representation, because the data frame had the same representation, the SQL had the same representation. And we do that using trees, tree structures. And let me give you a few examples of those. So how do you write this into a tree? So the first secret is that there are multiple kinds of trees. You have expression trees, and expressions are these fellows. So in this case, we have this join, but let's focus on the select. So we're selecting an ID. We're doing a little bit of calculation on that. We're doing a sum, and we are having some predicates. Those are all expressions. An expression is a computation on a value, or is a root value itself, and that's called an attribute. Other kinds of trees, there are also other kinds of trees. So now we look at the operator, so what the user wants us to do with in the program. So that would be these fellows. So we have like this join, a filter, a where statement, a projection, and another aggregation. That would translate into something like this. Notice how SQL nicely flips those two. So we're scanning data, joining it, filtering it, projecting it, and aggregating it. So, but for planning, we use actually two concepts. We have like a logical plan and a physical plan. Let me show you the logical plan. Logical plan only says, well, this is an aggregate, so I need to aggregate data. So it takes keys and aggregation operators. Projection just takes expressions. That's all structure. But it doesn't tell me anything about how to perform the computation. We don't get locked into that yet. One of the important things is that an operator tells me what it's going to output. That's actually all it needs to do. And we also reason about constraints. So, for instance, in this one, we know for sure that T2.id is larger than 50,000. We also know that T1 ID has to be larger than 50,000 because they're joined. A physical plan. Physical plan is, well, that describes the computation. So you can vary much more with physical plans than with logical plans. And it is executable, of course. And in this case, you see that project and filter aren't that interesting. They are about the same. You can only do so much with those. But for aggregation, you can actually choose between sort-based aggregation or hash-based aggregation. For joining, also, you can choose between sort merge join, hash shuffle join, and hash broadcast hash join. And you see that the tables all of a sudden have like their own dedicated scanners. The next thing is, well, we have these trees. Well, we have these programs and they're represented as trees. How do we go from one tree into another tree? So we need transformations. And a transformation is actually quite simple. It's just a change to a tree. We take one tree and we produce a new tree. And we can do that for expressions, logical plans, and physical plans. But you can also change a tree into a different kind of tree. And then you would change, for instance, well, in Spark, the only one doing that is actually logical to physical plan transformations. But you could also define other ones if you would like to. We do that by applying transforms to the trees. So every tree has like a method implemented, and you can just say, transform this tree, and it will produce a new tree for you. An example of this is this tree. What do we see here? This is the expression given in the example. 1 plus 2 plus T1.value. But this is not as efficient as you would like it to be, because, well, we're going to go and evaluate 1 plus 2 for each row. That's a waste. We can do this better. We can reason about this. We can just do that once and just transform it into 3 plus T1.value. And this is a tree transform. So next part is going to be a little bit more technical. We use, to implement this, we used the features in the Scala language that are algebraic data types, partial functions, and pattern matching. And each transformation is defined as a partial function. A partial function is kind of a special function. It has been explicitly defined for a subset of its input arguments. So it's only valid for like a range. If it's not valid, you can actually ask the partial function, can you execute this? And he will say yes or no. And then you can actually apply it. And if you don't, be careful, it'll throw an exception if the input is invalid. But that's very nice if you want to write transforms, and I'll show you why. This is the rule I just described. It takes an expression, it calls transform, and then you have this case statement. And this case statement does exactly what you want it to do. It's in case of the addition between one integer literal and another integer literal, we will just replace that add and its subtree by a single literal. So let's apply this rule. So you also need to know that the transforms are recursive, so they recurse down the tree. You can actually go both ways, up or down. Both have their uses. But we are going to go down the tree in this case. So we're first going to check if we can match the top level of this little expression tree. And so, well, the left-hand side or the right-hand side is an addition. It is an addition, so we actually hit this. but the left-hand side is an addition and the right-hand side is an attribute, and that doesn't match. So we go down a level. This, however, matches. We have a literal, literal 1 and literal 2, and we have an add. So we can actually fold the literal into one new literal. So, and that's a tree you get. Okay, so constant folding is a nice optimization, but it's not the only optimization you can do. For instance, SQL Server has over 800 of such rules. We have 50 or 60, but we're getting there. So how do you apply multiple rules? How does that work? So we start with a really nice one. This is called predicate pushdown. And what predicate pushdown does is actually it's looking for predicates. A predicate is an expression that has a Boolean result. So in this case, that means that this is a predicate T1 ID is T2 ID. That's actually a join predicate because it defines how the tables are connected, how tables T1 and T2 are connected. And we have a filter on T2.id. So we can do two things. And let's start with the coolest optimization first, and that's like the join predicate. This join has no join predicate, so we'll do a Cartesian join, which is super bad in terms of performance. But if we push down the predicate, we can do a very efficient join, and that's an inner join. And that is what's happening here. So we just move it down, and we get like a huge performance improvement. But we can do more. So we can also say the T2.id is larger than 50,000. We don't need T1 to evaluate this. So we also push this down below the join and just filter the data, the table 2 at the root. So constant folding. Well, I showed you this. So in this case, we move this one to that one. So 1 plus 2 plus T1 value becomes 3 plus T1 value. And T2 ID is larger than 50 times 1,000 becomes T2.id. Column pruning. So column pruning is a bit of so you can actually just reduce, improve your performance by doing two things. Either reduce the number of rows you're processing, or reduce the number of the size of the row you're processing. So the first two ones, the first one was reducing the number of rows, and this one is reducing the size of the row. And so what we do here is we are actually going to check what we are actually using, and only insert projections when we for the columns we're using. So let's say that T1 contains like five columns. We only need 2, so we just project them out and only select those 2. The same thing goes for T2. We only select T2.id. So before the transformation, we had a completely valid logical plan. We can execute this. It will be very inefficient, and after the transformations, we end up with a reasonably good executable logical plan. So this is what we do in Catalyst. A lot of these optimizations, so your program just gets faster, and you don't have to think about how it gets faster. So how do we combine those rules? We use this thing called the rule executor. And the rule executor just takes a bunch of transformations and puts them in batches and executes these batches. For instance, batch 1, batch 2, batch n. And each batch contains a bunch of rules. Typically, batches have like a general purpose. So, for instance, we have general optimizations in Spark, which run on a batch, but we also do like the rewrites of expressions we don't really support. So, for instance, aggregates with multiple distinct groups are rewritten into multiple aggregates. And but those are, for instance, in different batch. You only need to do those once. Every rule in here, so every rule, you have these rules in batches, and every rule has like a transform, so the function we saw before. And then we can execute rules in multiple fashions. So you can do a thing called fixed point. And fixed point means that you are going to apply one batch of rules over and over and over again until we reach this point where the rule, where the plan does not change anymore. And that's called a fixed point. Or we execute them once if you only need to remove nodes or do some validation. If we go to, so these were the transformations which were from tree to tree. And now we're going to do transformations from a logical plan into a physical plan. This is different because for logical plan to physical plan planning, we actually also want to know what you can have different options, right? So what we saw before is that with the previous physical plan, it's selected like a hash aggregate, but you can also have a sort-based aggregate. So you have different options, and that's why the mapping from logical plan to a physical plan is not 1 to 1, but 1 to n. And we call this, we apply so-called strategies. And every strategy does the same thing. It only produces it can only produce multiple trees. That's a big difference. So we do the same pattern matching. We use the same pattern matching magic, and we create different trees. Well, this is an example just taken from the Spark code. You see, we take a logical plan, and then we say, well, you have like this projection, for instance, this case, the first case here, and we just rewrite that into a project exec, which is like the executing node for a projection, and the same goes for filter. But for like joins, we have like entire join strategies in which we will look at like the size of the different tables. Can we broadcast the tables? How do they? And if we cannot broadcast, can we use a shuffle? Or else we'll use a sort merge join. And oh yeah, I forgot one thing here. If we plan bottom up, so we do the pattern match like recursively. So we call plan later, and that will actually just invoke another set of strategies. So the leaf nodes get planned first, and then we create like a plan from there. But this brings us to Spark's planner. In the first phase, we actually just use the strategies to create a physical plan. And that means that you can actually, that also means that we are going to do some selection of physical plans we want to use. And the second phase, we are going to use another set of rules, but this time the rules are a bit different. We use them mainly for correctness, and that we can actually execute a plan. So we use them for scalar subqueries. Those actually get executed before your actual query. We use them to make sure the distributions of your datasets are correct. So if you have like an aggregate eventually needs an hash aggregate needs the data to be partitioned by key. So we have all the keys of a single group in one partition. And ensure requirements does that for us. And we apply some pretty cool physical optimizations. So for instance, if we do exchanges, which are really expensive, then we try to do them only once. So if you have like a data set or a query that uses multiple tables, then you'll end up with, then we'll just do the exchange once and reuse the result. Let's just dive into ensure requirements for a little bit. So we have the sort merge join. Sort merge join, and we're not looking at partitioning right now. Sort merge join does, it needs sorted input because it actually just compares the inputs, and it's a very, very efficient way of joining. And so both T1 ID and T2 ID must be sorted. Okay, we check if the ensure requirements will just insert sort operators. So to make sure we can actually successfully execute the sort merge join. But hey, T1.id, table 1 has been sorted by ID. So we can actually just do a little bit of optimization here and just remove it from we can skip the sort and just continue like this. This is much more efficient, by the way. Okay, this concludes the first part, actually, of my talk. I'm a bit quicker than I thought. So, what shall we do?
If you have any questions, yeah, we can actually take it now for about 5 minutes.
Yeah.
There are 2 mics at the end of the aisle. If you have any questions about the deep dive catalyst analyzer, feel free. If not, then we can just continue. Yeah, just take the mic. There's a mic at the end of the aisle.
Does this work?
Okay, go ahead.
Hi.
Hi, over there.
Over here. So as with a lot of optimizers going back to the days of databases, you're able to pass hints to the query planner should it take a non-optimal route. Is that same feature available within Catalyst?
We have this thing only for joins. You can actually say that you want to broadcast a relation for a join, and then we'll broadcast it no matter what. And then but then you need to be careful with those because you might create an out-of-memory error.
Okay, thank you.
Second question, go ahead.
Hello, I'm here. When you implement query optimization and query plan and SQL like this optimization and Catalyst, do you implement it like from scratch, or do you have inspiration from open source libraries maybe?
So I know that there was inspiration from an article written in 2001, and I cannot name you it. This was developed as like a research project. Catalyst was developed by Michael Armbrust as a research project at Google. And his research was about creating a scalable optimizer. So yeah, it has been based on optimizations, yeah.
Okay.
We've got a question over here.
Yeah. So regarding the join strategies, I noticed your catalyst size when to do a map side join or a broadcast join. So what is the criteria you use? How do you know it's not going to run out of memory, or is there a specific size that your data has to be in order to decide to do that?
Sorry, could you...
Can you repeat the question? Can you speak in the mic so we can actually hear it?
Yeah, so the question is, what is your criteria to decide that you can do a broadcast join? How do you know it's not going to run out of memory?
So we actually have we collect a little bit of statistics for tables. So we know the sizes of the tables. We don't know the cardinalities, but we do know the sizes. So we can actually, based on the size, we first look if the size of the table is smaller than a broadcast threshold. That's usually 10 megabytes or 100 megabytes. And if it is, then we do a broadcast hash join. If the size, then we start comparing the sizes. So if the size of one relation is 3 times smaller, at least 3 times smaller than of the other relation, and the smaller relation will, if we partition it, will fit into memory, will fit into memory of the executor, then we do a shuffled hash join, and else we'll do a sort merge join. Does this answer your question?
Yeah, yes. Yeah, I was more into, for example, I do lots of them, but normally I know beforehand how much memory I have. So I have a 5 gigabytes broadcasting, for example. You have to increase some limits.
That's a big broadcast.
Yes, I have 40 gigs of RAM, so it's no problem.
Okay.
So sometimes I think, should I just leave it to Catalyst, or should I do it myself?
Well, I would leave it to Catalyst to start with, and if you're not happy, you can always inject broadcast hints. That would be my strategy.
Okay, we have another question over there. If you have a question, could you mind going to the end of the... There's a mic at the end. Yeah, on the left.
A question about join optimization regarding to the source. In your example, you have a filter and join with 2 tables, but you push the filter only to one source. So I know it's a case why the filter is not pushed to all tables part of the join.
That's just more, that has to do with the time I had for this presentation. Because you have this thing called infer constraints, and we actually push it down to both sides. If such predicates, if they are equal, then we can actually push them also down to the other side. So in practice, we do this.
That's new, because at some point I know the filter was pushed only on one side.
I think it has been added in 2.0, but...
Okay. Another question is about when some data source has, let's say, if you have a distributed data source, either a file system or even a database, so they have a partition scheme. In RDD, you can enforce the partitioning scheme of RDDs, but in DataFrame, it's not allowed. For example, for joins, if you have collocated keys between two tables and the data source behind know that, we cannot say it to Spark in order to optimize this kind of join. When is that planned to have this capability to have partitioning of the source?
So I don't, I do agree with you on that one. So this is about the data source API, and you can do a lot in that, but we are still missing like partitioning information and sorting information for that matter. We are planning to do like an improved version of the data source API, which is also a bit more, much more decoupled from Spark in like 2.2 or 2.3.
Okay.
But that's just, it's a dot on the horizon at the moment.
Okay, thanks.
Thank you very much. Big hand for Herman. Before I would take a 5-minute break before we actually start next section.
Thank you.